This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
A few more minutes. What was the last lecture was about?
Power gain circles.
Okay. So you're kind of finishing up on the microwave amplifiers? Oh, yeah. No? Okay. Yeah, probably Stan might have wanted to cover something more on that, but he gave me a kind of topic that self-contained, so I can talk to you today. I'm sure he will come and retouch on some of these as well. I think let's start. My name is Tasnim Malatis. I'm from the Electrical and Electronic Engineering Department. I used to teach this subject many years ago. So some of this content Stan might be using actually came from me probably as well. So this is content that I used to use, but I just updated something this afternoon just to bring a bit more context to it. So I'm going to use this lecture to talk about how do we manage nonlinearity in high-speed electronic circuits. Because most of your design so far, we would be treating as everything is linear, nothing changing, and therefore we can do some calculations, and the same way we can use some template circuits to realize some operations. But the reality is quite different. When you take any device, for example in RF, if you take a wireless device out of your mobile phone or any other wireless transmitting device, a very common device is called mixer. It allows you to convert your signal at one frequency into another frequency, so that it can, you can use the right licensed band or unlicensed band to radiate from wirelessly and then receive at the other end. That taking a low frequency content and up converting to a higher frequency, so before you can transmit, or when you receive from the antenna, down convert it back to a low frequency so you can process it with your digital circuits. That's commonly used by mixers. And mixers can be realized by different things, but in order to use that frequency translation, the trick is actually the nonlinear characteristics of the device. The most common device is the diode. That it is a nonlinear exponential transfer function. It has no linear, but we try to operate the diode in most of the times in where the linear curve is, but it has a nonlinear characteristics underneath it. So if you look at that circuit on the top, where you use 4 diodes in a balanced configuration, so that we can get an analog modulating signal at the x of t, and we can apply a local oscillator at the bottom port, then we can produce a high frequency signal at the output. Or the other way around, we apply a high frequency signal and apply a local oscillator, we can downconvert the signal to the other side. That circuit can be a bidirectional circuit. And you will now see that the device actually needs nonlinearity to do the frequency translation, and therefore when you do operate those things, you need to know how that nonlinearity impacts your performance. All right. Or a very simple mixer could be just a basic BJT, because BJT is, again, is a junction of two diodes in a particular configuration. So the diode's exponential characteristics comes in the BJT as well. If you bias it in the place where the diode is turning on and off transition, then you can create a kind of frequency or nonlinear transfer function that can mix two signals and then create a difference or a sum of two frequencies. So again, that device has a nonlinear transfer function because BJT has an exponential underlying characteristics. Or we can take a PN junction, reverse bias it, it becomes a capacitance. Depending on what bias voltage we apply, it gives you a variable capacitance. So if you want a filter that you want to tune your frequency from channel A to channel B, you want a varactor. That's you, by changing the voltage, you can move from center frequency from A to B and select the channels, for example. So that's a type of circuit that normally people call varactor, which is essentially a reverse bias diode or PN junction, and you apply a bias that gives you a variable capacitance, all right? And the variable capacitance in a inductance capacitive network gives you a filter function which can be tuned, either bandwidth or a center frequency. But if you look at the varactor's capacitance versus a function, it is not a linear curve that you can use. You can see it is kind of hyperbolic characteristics. Most of the time we operate a circuit over a short range, therefore we assume it is linear. But once you operate the circuit over a large voltage, that assumption no longer holds. So then you need to know what will be the impact of nonlinearity. So essentially that's what I'm talking about. The devices that we use in most of the high frequency electronics, and sometimes we actually exploit the nonlinear characteristics to realize functions. Therefore the nonlinearity is unavoidable. You have to manage it. What are the impacts on other parts of the circuit? So this lecture is about just taking you through very quickly what is nonlinearity and what the manifestations of nonlinearity when it comes to the performance of your electronic systems, and what are the basic kind of parameters that you may want to either test or characterize when you're obtaining a chipset from one supplier and then you're building a cascade. You need to know how the nonlinearity from one system, when it is cascaded, is leading to an potentially adverse impact on your overall design. You may not meet what your specification is about. So that's really what I'm going to talk today. Just taking you through one at a time some of these points. So essentially in electronic systems, I guess we are putting an input and passing through either device or a cascade of device or a system to produce an output y of t. And when we're talking about these devices having a nonlinear characteristics, the simplest way to capture that would be a Taylor series kind of polynomial where output is a polynomial function of input, all right? So y of t, the output, now can be expressed as a series of terms which depends on the powers of the input signal. And the first term is essentially it's a DC shift, whatever the electronic circuit is producing by adding a bias voltage. If you didn't block the DC signal, then you will have the DC term. Then you have the first term, which is a linear term because the A1 is not dependent on anything else. It's a constant, so output is some multiplied versions of the input. So it doesn't change anything. That's called normally linear term. Then you can see the output second term, which is the square of the input per signal, which means if the signal has lots of frequency components, in the process of squaring it, you can put two sinusoids inside the x of t and see what will happen. Sine squared omega 1 plus sine squared omega 2t, and then 2 times sine omega 1 and omega 2t, then you will see the mixing of frequencies or doubling and tripling of frequencies. Same way the third order term also. So it actually goes all the way to 5th, and in some circuits up to 7th we need to worry about, because that's the nature of that circuit is, all right? And sometime mostly everything will be 0, but 1 or 2 of them will be very dominant, and therefore we need to know. And so there are largely, you can see a kind of odd terms, which is a linear terms a1 of x, and then a3 x cubed, and so on, or the even terms like, you know, square a2 and a4 and so on. And they lead to slightly different mixing of frequencies. As a result, that's one of the things we need to be worrying about. From a, you know, if you go back to your, you know, high school mathematics, essentially if you wanted to know exactly what coefficients out of that, if you can do a range of measurements for a given range of different input values, you record a range of output values, and you basically go through this, you know, second order derivative and third order derivative, you will see this is actually right. When the input value is 0, that coefficient A3 can be determined by knowing third order differentiation of that term. Essentially, that's how the Taylor series are defined, right? So we're expanding around value x equals 0. And you can expand that over any value of x you want, x equal a or x equal b, you can do that. So if we do a series of measurements, even if you don't know the black box or you don't know the inputs, the circuit composition inside, one can figure out what is the overall input-output characteristics, and then therefore can measure something. So it's not always you need to know what the internal circuit is look like. You know, if you wanted to quantify the nonlinear performance of that system, you can do a series of measurements and work out what is inside really doing. You all with me so far? So let's change the things. In most of the high frequency electronics, we are not putting a simple signal X, but it has a multiple frequency content. We put it through the circuit to process that frequency content. Therefore, let's kind of start with the most simplest things. We put a sinusoidal frequency signal with a frequency of omega or f, depending on what you're comfortable with. And you put it through this signal, and you can see what happens. Right? Immediately, you can see second harmonic being generated as a result of the second order nonlinearity. And third order harmonic is being generated as a result of third order nonlinear coefficient that we had seen on things. But if you look at the output signal, if you look at the fundamental signal, that's v times cos of omega t as it goes through whatever the output value of it, because you can, when you expand all of them, in all of them there is a cos omega t, and then it comes out that the gain or the constant that is linking input and output will be the input voltage V times whatever the amplitude of the output signal. And you can see there's a linear term which we think that circuit is usually we do, plus other terms as well from the nonlinearity. So, okay. So once you can see, once a circuit has a nonlinearity, even the gain or a multiplier is no longer just determined by the first order coefficient A1, but it's a third order also add to the power in the fundamentals by way of mixing it. And what happens is, as your input voltage, and you see the output or the gain, which is linking the input voltage to the output voltage, is now suddenly function of your input magnitude, right? That means as you increase your signal at the input, your output gain is changing, right? And why it is, because there is a constant energy transfer from your fundamental signal component, that's what is going into the circuit, into all other higher frequency components of 2 omega t, 3 omega t, and so on. This is okay for a single sinusoidal one frequency excitation. As you know, most of your signal is broadband, will have finite frequency content. You can then write now the input signal is a Fourier sum of number of frequency contents, and therefore you can see how clumsy this simple expansion turns out to be. Therefore, nonlinearity can be a significant headache if you don't manage that in your design, especially when you have a wide frequency bandwidth going into the input of the circuit and then you're doing a lot of nonlinear transfer function based. And nonlinearity can be avoided in most of the RF circuits because that's the exact nature of a characteristic that we are exploiting, either in the reverse bias junction capacitance as a varactor, or a diode or a transistor as a function to frequency translate. That nonlinearity is what actually gives you that frequency translation, therefore you can't avoid it. You just need to know how to manage it. So you can see now there is immediately one problem, even though you may have designed an amplifier with a gain that is proportional, that remains constant, supposed to be according to your design. As I change the input signal, it should produce a proportional output signal with a multiplier G that we wanted to produce. The one that I've just shown you, once you have a third order nonlinearity inside that black box, your output gain is a function of the input voltage, and it actually goes up to almost linear up to some point, and then you no longer can keep amplifying it. The gains start to saturate because of that term as a function of V squared on the top, all right? So it is now becoming a function of input voltage rather than a constant. So you can see now just purely from a gain, converting an input signal into a larger signal itself can only work in a linear form up to a certain point, and after that it gets to a compression. We call that as a compression because the gain is no longer remains constant, it's actually declining, so it's being compressed down. That's why it's called compression. All right. And of course we need to know, because this is an important characteristic in a circuit with an amplifier, you need to know up to what point that amplifier acts as a linear, so that you can rely, by changing the input signal, you will see a corresponding change in your output signal in a linear term. All right? And therefore, most of the circuit, when you're designing an amplifier or you're buying an amplifier, they will have to specify what is the compression point. So you can see, how do we measure it? We need to have some standard way of measuring it. So the standard way in the industry is called 1 dB compression point. That means the gain, which is a linear gain, goes down compared to the linear gain by 1 dB. What is that point is called 1 dB compression point. So you can see the linear curve extended, and the real curve is kind of saturating there. When the point of separation between the linear extrapolated curve and the actual gain differs by 1 dB, the corresponding input point or input power is called 1 dB compression point. All right? So in essence, you will never exceed your input range beyond that point, because then, unless you don't really care about nonlinearity, then you don't want to, because you don't gain anything in the gain terms, and you create more problems in terms of harmonics being produced. So it's a very, very common specification. If you open up an RF amplifier, when you go home, Google it, find it, you will see a compression points mentioned. And that gives you an indication as, okay, up to what point I can play with this amplifier, right? It's an important parameter for you to know before you start applying something. Because if this the actual power that you need the amplifier to operate is here, it doesn't going to work, right? You need to keep looking for that compression point further down. So just to kind of give you a little bit more back to what we originally had, remember the gain of the stage we defined as a G, and then I wrote down a function, for a given sinusoidal excitation that was a function of input voltage. And what it means is the linear curve is simply the V is equal to 0, that's actually G of 0, and whatever other arbitrary value is only differed by 1 dB. So I'm just simply reinterpreting the definition of 1 dB compression point in the first line, all right? So I'm just simply saying the power of the linear gain, which is a G of 0, which doesn't have a voltage dependent value, minus whatever the value of the instantaneous gain at a particular voltage value of input, must be equal to, in dB scales, that's why I'm taking 20 log on both sides, should be equal to 1 dB, all right? And therefore now I can rearrange this, and remember the log differences in this way can be as a ratios of G0 over GV, and that comes out to be this, and equal to 1, and then you can check again the real value for V at which this is actually meet. Well, I'll leave you to kind of exercise whether you can take a exponential on both sides to work out what is V2 is going to be, but it works out roughly this value to be equal to 1. You know exactly what this value has to be, and therefore you can work out, it turns out it with some constant time, the two ratios, A1 over A3 here, that includes the 4 over 3 is there as well, which is a square of the value, so then you need to take a square root in order to get the value. So if the signal has two signals, this is we only assumed one input signal going in, and we looked at what's the gain being compressed, right? But if we put two signals of two slightly different frequency, the same kind of mixing thing's going to come up in a different way. And so just to complicate this, now the same transfer function, we put now omega 1 and omega 2t, so two sinusoidal signals are going in, and for the simplicity we say both signals have the same amplitude of V, all right? So so V1 and V2 is equal to V, and then you can expand this. You can either type in Mathematica or something. You can type in and it expands it for you if you don't want to expand it yourself. But what it is, it creates the fundamental terms of both signals, omega 1 and omega 2, and you can see that the fundamental signal roughly has the same the value that we have seen before, and now we have second order terms where there is lots of different frequencies, second harmonic of omega 1 and omega 2. Sum of those two frequencies is omega 1 plus omega 2, and difference of those frequencies, and then 2 times 1 minus that, and so on. It goes in lots of different things. So these are called third order terms because there are 3 frequencies are mixing up. They are second order because there are 2 frequencies are mixing up, and the other one is fundamental because there's only one fundamental signal is there. All right. So as we expected, the coefficient in front of the gain of this fundamental signal, same as what we had before. But here I'm trying to highlight there are more mixing of frequencies coming up. All right. So you only put 2 frequencies. Because of the nonlinearity, we just created so many different frequencies. All right. And that's exactly what a mixer is. All right. You put an LO signal, a low carrier frequency, and a low frequency signal, and it's a nonlinearity produces a mixing either up or down, and as long as you choose, this is down conversion, means you subtract the frequency of high frequency down. This is up conversion because you're summing up 2 frequency to generate higher frequency. So these are the 2 terms often used in mixers. This is down up conversion, this is down conversion. And the second harmonic and this one we need to try to minimize if possible, otherwise they can cause issues. Can someone tell me why second order terms may not be as of a problem than third order terms? Let's say we're looking at a RF circuit with signals which are closely aligned frequencies, all right? So, let's say 100 megahertz, 105 megahertz together. And in that circuit, second order term may not be as of a headache compared to the third order term. Can anyone tell me why it is?
It might be easier to filter the second order than the third one.
Yeah, because if you have 101 megahertz and 105 megahertz, the difference is 1 megahertz, am I right? And the sum of it is 200 megahertz. Both of them seems to be on both sides of the required signal band. So if I have a nice filter, just looking at the required band of 101 to 104 megahertz, I can ignore the second harmonics. But if I take 2 omega 1 minus omega 2, it comes back into the fundamental frequency band, am I right? 2 times 101 minus 104 is roughly somewhere there, and then the other way around, all right? So the third order mixing terms produces frequencies which are very similar to the fundamental frequencies, and it can't be filtered out, all right? So therefore, third order terms is a big headache. If you don't need them, it can be a big headache. Of course, if you design a circuit where the fundamental frequency and second harmonics is within one band. For example, if you're designing a very broadband antenna which is looking from, let's say, 1 gigahertz to up to 6 gigahertz. We want one antenna which looks at all the mobile systems and Wi-Fi and everything. Let's say we want to design we want to digitize everything out there and then know who is transmitting what. Let's say that's a hypothetical situation. So in that case, we want an antenna plus amplifiers which is looking from anywhere from few hundred megahertz all the way to 5 gigahertz, so up to 6 gigahertz, right? So you can see 1 gigahertz and twice that is 2 gigahertz is part of it, and even three times is part of it. So in that case, second harmonic, third harmonic, even fourth, fifth is becoming an important, because all of them fall into the same frequency. So as the kind of earlier suggestion before, when you have the kind of key signals, omega 1 and omega 2, that third order terms comes very close to each other. Therefore, it cannot be easily filtered out. And some of them will fall on top of each other. And whereas the second harmonic or the difference frequencies can easily be filtered out. So there is no, so how do you know how many of these things are going to be in a circuit? It really goes back to that nonlinear transfer function and the gain that you have, right? Remember, the nonlinear transfer function tells you A1, A2, A3. If the A3 is very large, then it's going to produce a lot of components. If A5 is almost zero, it's not going to lead to more components. So it really depends on what that nonlinear characteristics and how much gain you're putting in later in order to know how many of these components are going to be produced. So, even though we wanted the F1, F2, or omega 1, omega 2 as the only circuit that's needed, signals that we're interested in, but we can't ignore all the different signals coming out, third order, fifth order terms. This is 5 frequencies mixing, is 3 frequencies mixing. They're all roughly same things, and therefore they need to be managed. And we need to know when we design, we can tell other people up to what point this is a headache for you, or when you're buying someone else's system into your system, you need to check whether their design is actually will not give you any headache further on. All right? So that's the 2 reasons that you need to be worrying about nonlinearity and harmonics. So these frequency components are called harmonics, and the distortion these signals introduce into your signal is called intermodulation distortion. Intermodulation means those modulation frequencies are mixing up together to give you a signal which is roughly similar frequency as your interested frequency, and therefore that is called as distortion on top of your wanted signal. So third order intermodulation is a one major thing that normally you called in to manage, and I already told about the second harmonics. When the frequency bandwidth it doesn't include the second harmonic, it's not an issue, it can be filtered out, but the third order things we need to know how to both design with minimum third order intermodulation, but also know how to manage other person's third order intermodulation distortion. So here you can see some of the things as the intensity goes up, your fundamental frequency will go, for a 6 dB change in the fundamental signal, after a certain point, you're actually creating more change in other harmonics than in your fundamental. So the fundamental signal only go on 6 dB, whereas all other power is being transferred into third order and second order. You can see the second order is gone by 12 dB, and third order has gone by 18 dB. So beyond that 1 dB compression point, this is what's happening. Your input signal energy being used to convert into new frequency components, and all of the energy is going into these components, but not into the signal that you want. And that's just actual plot of a measured thing. So this is the fundamental, and you can see the third order intermodulations. And one thing you can also see, there is a noise below that, all right? So why the intermodulation issue is because normally we only look for signal and noise, And as long as signal is well above the noise, we're happy. But now you can see the intermodulation is well above the noise, but that's actually going to distort your signal. So we need to worry about how to do it. So as the same as the 1 dB compression point, a common way of knowing up to what point this is not an issue for me, up to what beyond what point it's going to be an issue is these called intercept points is normally plotted out. And it's very similar to the compression point. So remember the linear curve I told you, the gain, this is your fundamental signal, amplitude is plotted, so the input power is increasing, output power on the vertical axis, and this is your gain formula, as you can see, go there and then goes into compression, and you can see the 1 dB defined at the P1 point, that's 1 dB compression point. But if I now look at and go on for a 2 frequency excitation, if I plot what is the power of the third order product, and I plot that one as a power as it goes increases, it doesn't start here because the third order intercept doesn't start to appear until you increase your signal level, right? And then after some point, the third order intercept will appear, third order products will start to come, and you can monitor the power and then plot it as a function of input value. It also goes something like that, and then start to go into compression. Just coincidentally, these two curves meet at the one point. That's not the case for any device. I think it's a very poor example. I'll show you one that doesn't actually do it. And same way we see this, if this curve is linear, it goes there linearly there, but it actually starts to compress. And if we look for intersection of this curve and the linear curve, that point is called intercept point. That means at that point, there is an equal amount of power in your third order intermodulation as well as your fundamental intermodulation. So that's kind of the absolute limit, right? Instead of just applying your fundamental, you just apply, you're just creating equal amount of power in your intermodulation distortions. And noise is somewhere below here, and if the more noise is higher, then we need to worry about noise. The noise is below, we need to worry about the intermodulation distortions. Can you see the picture now? There seems to be a sweet spot somewhere here. I don't need to worry about the intermodulation because hasn't come up. And that's kind of the area that I need to get my circuit work. All right? If I don't work it here, then I will have to worry about this intermodulation. So remember that intermodulation. I'm simply summarizing the things that I showed on the thing. Intercept point is normally called P3, so if you're looking for specific data sheets, then you look for P3. And again, P3 can be shown by looking at the Taylor coefficients as I showed you before, but most of the time it's measured because we don't want to rely on some mathematical interpretation because that transfer function may not be known, right? We need to measure it and quantify it. And so what I was trying to lead to before, there seems to be a sweet spot where the intermodulation is not there, and I can get almost linear gain. That's what I wanted to operate. And in electronic design, there is a parameter normally often used to characterize safe operating range for your system. It's called dynamic range. All right? The dynamic range, just be careful, it actually means different things, depends on what you design, even within electronic design. If you're designing digital system, it is about the voltage, low to voltage high separation, how much it is there. And in the analog sense, dynamic range can be lots of different things, all right? So there are lots of different types of dynamic range people will use to differentiate what they mean. But in all cases, it somehow gives you an operating range over which some parameters manage well. That's what it means, all right? So in this case, often the dynamic ranges can be used simply to tell you what is the safest gain range over which you can do. That's actually the value up to the 1 dB compression point is where the linearity is maintained. So that is one dynamic range, called linear dynamic range. Simply tells you how much is the 1 dB compression point, that is the power at which the gain it drops by 1 dB, less how much is the noise, okay? Because that actually gives you the dynamic range. So you can't amplify, you can't detect any signal below the noise, You can only detect the signal above the noise, and up to what point before the compression kicks in, that's your linear dynamic range. So your RF circuit that you designed now can work from over this power range. When the input power range in this range, you will be able to get it to work because it is above the noise but below the compression or non-linearity point. So this is one way of defining a dynamic range. Let's now put all of them together. Noise, intermodulation, everything into the picture. Now it starts to complicate a little bit more. So remember that we have these two triangles kind of things. So you have the gain or the linear curve. This is your third order intermodulation products term, and the noise is over there. All right. So if we wanted to characterize your design or check your as devices, we wanted to know what is the dynamic range for each of the device, taking into account of the noise as well as the intermodulation. So not just the linear range as what we looked at it before, it's really how much operating range we can get, okay? So there are a number of ranges that we can define. One is here where the intermodulation is almost same as noise and the signal can operate up to that point, all right? That is a one kind of dynamic range we can mention. That means we don't want any intermodulation at all. Or we can say we tolerate some amount of intermodulation, but we can actually well above the noise and the 1 dB compression. This is your linear dynamic range. And so we wanted to define a further kind of measurements in order to include the intermodulation distortion in our characteristics.
So, excuse me?
Yeah.
If the intersect point is not in the dynamic range, like why do we care about it? The intersect in the one.
The last one?
The last one.
Yeah, so that's just coming up.
Oh, okay.
So that's when I didn't put it in there. So then now, remember this one is your linear dynamic range, right? This one is almost, you can say, I don't want any intermodulation distortion. That's your kind of another range. But what is normally commonly worked out is how do we deal with that intercept point and a new kind of range. That's what I was going to be about to say. So just before I won't go into that, one thing I wanted to tell you a little bit about it. There is something problem with this because these are power levels of individual frequency components of very narrow band value, which is easy to measure, right? But this thing, noise, is a white noise, a very broad band, all right? Depending on what you plug in, this noise level will be different. So how the hell are you going to get a very uniform way of defining where is your noise level is? Because spectrum analyzer A that you put it in will give you a particular noise floor, and then you go and put it in another lab, it will give you a different noise floor because what you're measuring, not just the circuit noise, plus whatever your instrument is also noise. And also it's over whatever the bandwidth of the circuit, all right? Because if the circuit is 10 megahertz, it will give you a one noise level. If it is over 1 GHz, it's now going to give you a different noise figure. So when you're designing circuits of different frequency bandwidth, there is no easy way of dealing with noise because it is bandwidth dependent. More bandwidth, you have more noise, right? So in order for these kind of things, this noise floor is not any arbitrary noise floor that you see on the instrument. It needs to be normalized to 1 hertz of bandwidth. That's only when we have one unique way of telling how bad the noise is, right? For all these measurements, we don't take what is the absolute noise. We look at it, okay, what is our interested bandwidth? Are we designing a gigabit transceiver or a 100 meg receiver? 100 meg is our bandwidth. Then we divide the noise by the 100 megahertz and find out where the noise floor is. That's the noise floor per hertz of bandwidth, all right? So that is the only way we can measure. And then everything is measured over a per hertz of bandwidth power measurements. Then everything is kind of looks the same measurements. Then we can rely on simply knowing what the intercept points are. Otherwise, it can lead to really different things. Just wanted to emphasize that before going into the new range. And the other thing is, when you're doing actually these type of intercepts, as we said, many circuits may never go to that find of intercept points. You will actually kill it well before that actually intercepts. So it is actually an hypothetical intercept points. It's not a real point where you can actually plot it and show it and react, okay? So the real device might only work up to small amount of power and then compression point hit. Same thing happens for the intermodulation product as well. Very small range it will operate. So how do we deal with these intercept points? We just use the linear curves and then I basically extrapolate and find the intercept point because it is a way of one consistent way of measuring and quantifying. That's the only reason. But the actual intercept point will be meaningless for the real powers because you will never reach that point in practice because most devices will get killed by that time. All right? So just be mindful when you plot something, it comes up like that. Don't think that you got something wrong because it's just a device that will always operate over narrow range. But then you need to be very careful. There's enough measurement for you to extrapolate. Otherwise, they all go haywire. Just few kind of things to worry about. So when we plot these intercept points, even if you have the finite, so the device only works up to that point, and we extend it and work out that. So there are a couple of points to note again. You can see here, the device only works up to there. That's where our compression point dynamic range will come in. But now, if you wanted to work out power range of the input when the distortion is free, this is actually the dynamic range of the power levels from here where the signal is starting to be above noise and linear up to the point where the intermodulation starts to pick up, and this is your range that is important. And you can see this range has something to do with the intercept points. If you use two triangles, you will see there is a direct relationship to the height of that intercept point and to that range. That's why it's important to find that intercept point. Might just probably have it in a different way. I thought that there was a diagram there. No, sorry. Okay. Let me go back to the one that, okay. So you can see, there is two triangles, that one there and one here, all right? And that intercept point, if you know that intercept point, and if you know the noise value, then you can actually work out this dynamic range. That's why the intercept point is important. And it turns out, maybe check it out, with that, it turns out that spurious free, that means intermodulation free dynamic range, is simply 2/3 of the intercept point minus the noise of it. Can anyone think why that 2/3 comes in? Think of those two triangles and the slope of those triangles. I might just bring it up back again. This is a slope of 1. Okay, linear terms, it will be a slope of 1. And the third order intermodulation, the slope is 1 to 3. All right. So these triangles, almost like a 2 to 3 ratio in this bottom base for the same given height, and that's the one that leads to that 2/3 of P3 minus N0, which is that height of that intercept point. So, and as I said, the definition, if you look at the units of that dynamic range, it will basically mention that whatever the dB of power, because it's a range, we are looking at a logarithmic difference of the power levels, but divided over hertz of 2/3, because of the 2/3 is there. It comes because the noise is now divided by the bandwidth, and the noise is the noise density, not the actual noise power. And that's why the hertz to the 2/3 comes into the unit of it. And so when you're looking at it, you will see it. So if you want a device or application, there's a particular SNR target, then you can work out what is the dynamic range, because the signal, the range that you get has to be above the SNR, the required SNR. So this is your target dynamic range you're trying to achieve, because this is a minimum that you can tolerate, and this is the reality of the intercept point. So the difference between the minimum that you want is your dynamic range. All right. But in many times when you're building it, you're building a filter and then a mixer and then a filter and an amplifier of sort low noise or high gain depending on where it is. What we're doing is we're basically building stage by stage and cascading it until we get to the function that we want. All right? So any electronic circuit can be thought of it as just a cascading of multiple stages, and we just need to know this same nonlinearity check need to be applied to every stage, but also need to do it over the whole stage so that we know that overall performance hasn't been compromised in it when it comes to nonlinearity. So you can kind of easy to do a single stage. What we have done so far, it's easy to see. We can simply put two frequencies, do some measurements, and then we can work out the IP3 or P3 intercept, and from that we can work out what's the kind of the dynamic range we need. But when you're doing multiple stages, we need to know how to generate this. And have you done the Frisch formula for a gain? Like, you know, you have a cascade of gains, how it is. Have you done that yet? Okay. So you haven't done the amplifier cascades, how to calculate noise figure and all that yet? Okay, so he's probably talking about noise next stage. And you will come to a formula where how do we deal with noise accumulation over a cascades when you have different gains. And there is a formula for that to indicate that. So people were very keen on how can we develop that kind of rule of thumb formula for a nonlinearity so that we can check, you know, every stage whether it's actually meets the specifications. I'm not going to derive that here, but essentially it comes out something like this. So if you know the intercept points of individual stages, you can kind of work out using this formula to work out what will be the cascade of the two amplifier chains, G1 and G2, and overall IP3 will be given by first nonlinearity, second nonlinearity divided by the gain of the first one, and so on. It goes on if you have cascade. So you will see the same pattern of formula will be given to you for the noise matter. That's why I tried to give you this. But if you want, I can give you the reference for achieving it. But essentially, that's a very useful trick to quickly check. If you know exactly individual blocks, what is the IP3s that you have quantified, then you can check for the whole stage whether it's actually going to lead to you know, scope creep or a specification not being met by doing this type of calculations. Essentially what we're doing is we're just taking those intercept points, as I tried to do it over there for a third order term, looking at the amplitudes and then working out what is the actually final P3 will be, and then realizing that it is in this form, and that's what I've just done. This is IP3, and then IP3 divided by a gain. So that's what I've done there. And you know, I don't think Stan would expect you to remember how to derive it, but I was just trying to give you a context over which how you can use your intercept point kind of concept at a single device or a subsystem level, and then how you can cascade it to multiple things and then work out. Whenever you needed it, if you just type in this intercept point of a cascade system, you will get to the paper. But I will see whether I can send it to Stan. He can put it up on the things as to what's the origin of this design. But I think given that Stan hasn't done the Frisch formula yet for the noise, you might not see the value of it, because the noise calculations will have a very similar things, and then you will see that this is very much the same template. So then you start to appreciate the value of it, because it's exactly the same kind of intuition applies here as well as the noises here. If I had known it, I would have put that one before telling you so that you can compare it. So what we're looking at here in a summary kind of things is if you will be designing a cascades of systems. Some of them will be gain, some of them will be loss. It doesn't matter because we just generalize by gain. If it's lost, it's negative, or less than 1. Otherwise, it's greater than 1, and so on. So you can deal with it. And in the IP3, if you know exactly individual subsystem and their intercept points and their gain things, we can then plug in this cascaded system formula. What it happens is, I think the takeaway message, maybe I just wanted you to have a look at it, what is actually telling you, and tell me in your words what you understand by that bottom formula. What do you take away from it? Don't worry about it, you don't have to remember it, but what is intuitively telling that formula to you? Something about where you need to put your effort in managing the IP3. So what it means is it's the IP3 of the first stage comes in as it is without any multiplication of gain 1, gain 2, anything, right? Any other system is multiplied by, or the scale down by the gain of the preceding stages, right? Or a cascaded gain. So this is the third stage, you've got the jth stage, all the gain preceding the gain j minus 1 will be scaling down that value, all right? Essentially increasing this contribution, all right? Because if you assume this is greater than 1 overall, then it will be increasing it. So you can see the intercept point of the starting point plus all the scaled versions of the intercept points added to that. So the last stage is going to be adding a lot more contribution because of the fact that you multiply by lots of the gains and then putting it in there. In the noise case, you will see the first case dominates the noise figures. That's why we want to put low noise amplifier at any of the start of a cascade and then try to manage signal. And the intercept points, the last stage does matter a lot of it as well. So it's easier if you put it in a couple of numerical examples and then see how it is, or 2 or 3 stage, and see how it is. And it's a very powerful, useful formula to know when you have a couple of different IP3 stages you're combining. Very quickly you can see where the trouble spot is going to be. All right. That's pretty much I had to cover, and I'm sure when Stan talks about noise, there will be almost an inverse of this in terms of the noise figure. You will see it, and that's the 2 distortions that you need to manage when you're looking at cascade. So I'll see whether I can add a reference to this, the last part of it. I don't think he would expect you to know how to derive it, but it's a useful knowledge to have it when you're designing, if you ever have to design a cascaded RF systems. I think that's all I have. Any questions? Comments? All right, all the best. Thank you.
place of all